welcome back everybody. My name is Mirko Coggi, and today I will talk about my research on pangenomic analysis. So before starting, some few notes about me. I'm a PhD student here in Politecnico di Milano, and I'm also the co-founder and IP strategist at Genogra, which is a startup I founded last year with some colleagues, and where we are building software for genome analysis. And in particular, my research interest focus on computational genomics, genome graphs, or better, pangenome graphs, and hardware acceleration, which I discovered through my biomedical engineering background. So, talking about genomics has a lot of application in many different contexts, ranging from personalized medicine, radiogenomics, metabolomics, agrogenomics, and many other context, but despite this great amount of application, we can see that the genomic pipeline is pretty much standardized, because it always starts with the taking of the DNA sample, which is then sequenced to obtain subsequences of the original genomes, which are called reads. Then the computational tasks begin, because these reads need to be assembled together to recreate the original genome, which finally is analyzed to find a specific pattern or specific genes inside the original genome. So until the 2015, both the computational task has always been supported by a linear representation of the genome, which however limits the scalability of population studies because of the redundancy of the data and the inefficiency to represent the structural variations. For this reason, genome graphs, or better pangenome graphs, has been introduced as a new, more compact and efficient way for representing the inter- and intra-individual variability, because of their intrinsic ability of representing variations among a population of genomes as alternative paths inside a directed graph. However, introducing this new, more complex structure in the computation introduced new technical challenges when developing pangenomic pipeline for the genome analysis. And one of the main challenges is the sequence-to-graph alignment process, which consists of mapping a sequence of nucleotides to a pangenome graphs, or better, to a path in the graph, maximizing the alignment score among the two structures. And during my research, I analyzed lots of tools in the state-of-the-art which account for this process, and I identified that there is a lack of a definitive solution which can perform better on different type of data. For example, I found some tools that can go faster on more linear graphs, other on highly branched graphs. Then there are lots of parameters that can modify the way we are aligning the read to the graphs. And this helped me in defining the scope of the goal of my research, which will be the creation of a definitive framework for genome graph analysis. In particular, I identified 3 steps: the pre-processing of the data, the application of the read mapping and variant calling, and after that, the post-processing of the result, which can draw the end user, so the bioinformatician, from the very raw data after the sequencing step till the application of machine learning tools for the interpretation of the data. And in particular, the first step, the pre-processing of the reference graph, starts with the identification of repeated regions, which during the creation of the graph can lead to misrepresentation of the repeated region. And so I created a tool for identifying this type of misrepresentation to improve the morphology of the input graph. After then, since we are talking about very, very large data, when we talk about genomic data, the input graph can be very, very big. And for this reason, I introduced a step of graph partitioning to break the original large graphs into smaller subsection, smaller partition with specific characteristics, so more linear areas and highly branched areas. Then there is the application of the best sequence to graph alignment tool based on the characteristic of the partition. And here we have a parallel execution of the sequence to graph alignment process, because we can apply the alignment over multiple partitions simultaneously, but there is also a second level of parallelism, because we can also align multiple reads to the same partition at the same time. And after that, we have the parallel variant calling step which characterize each variation found during the alignment process. After that, we have the post-processing with the merging of the outputs of the variant calling step, which are the VCF files, into structured data frame, which finally can be filtered and queried with a specific tool. And this can help us in identifying only specific variation that we want to account during the application of machine learning tool for the interpretation. So, taking everything together, there is this framework composed by 7 tools. Of course, as we need to be the most performant as possible, each tool is created using low-level programming language and where we can also hardware acceleration, but we know that this can lead to difficulty in the use of the framework for the end user. For this reason, what I want to create is a Python binding of the whole framework to increment the automation of the whole framework and to make more easy its adaptation to the already used pipeline by the bioinformaticians. So, to recap, what I've told today is the framework for a high-performance framework for genome graph processing, which can also be very, very easy to use and can fit effortlessly the standardized pipeline. And what I'm looking for is collaboration with a bioinformatician which want to test my framework in their use cases and also to help in defining new tools that can be helpful for their everyday work. So with this, I concluded. Thank you for your attention.